already. Thank you for having me. So what I want to talk about is the science in the spaces between disciplines. So Dane, I feel like you really set me up. This is a perfect segue. Thank you so much. I think, as just previously mentioned, that the frontiers of science are no longer really defined solely by new discoveries, but by how knowledge connects between and across disciplines and informs decisions that we need to make. And I think we've shifted from isolated fields to integrated systems thinking, and there's a growing interest in not only understanding how the world works, but how the knowledge is connected and applied in such a complex and interdependent system. So to illustrate this, I want to take a closer look at this photo. I asked a bunch of scientists what came to mind when they looked at this photo, and I got a wide range of responses. I want to go for a swim and drink cocktails. Looks like a great holiday spot. Is there gold at the bottom of the waterfall? I see mindfulness. Are there crocs? I think someone in the audience might have said that one, Karen. I'd love to go for a swim. Reminds me of Sri Lanka, and I think I'd get sunburnt. So I think there's a bit of a theme, and that theme is an appreciation of this location. But then I asked them to look through a professional lens, and we got some interesting responses. So if we have a look at it from a physics lens, we see solar angle, light scattering, rainbows. If we look at statistics, we've got microclimates and time series variability. Synthetic biology might look at photosynthesis and energy capture and the role of rubisco. And if we look at ecology, we've got primary production and food webs. And what this demonstrates is that energy moves through everything. So energy enters the system as sunlight. The physicists might focus on how that light bends or scatters to form the rainbow in the spray, but that same light is also absorbed by the plants around the falls. At a molecular level, the photosynthesis uses that energy to fix carbon, turning light into stored chemical energy. And then where the water flows and where the shade falls determines how much energy is available, and that will create tiny microclimates. Those small differences then influence which plants grow and where, how productive those plants are, and then which insects and animals that they can then support. And then statistics allows us to see these patterns over time and reveal that energy availability is uneven, it's dynamic, and it's tightly linked to both the physical and the biological processes. So the same energy creates optical phenomena, drives chemistry inside cells, and shapes entire ecosystems. If we have another look, a water engineer might look at velocity and supercritical flow. A sedimentary geologist might look at horizontal strata and tectonic stability. A climate scientist looks at wet and dry season intensity and water quality. And the statistician, again, pops up, they're everywhere, looks at long-term averaging and extreme events. And here we see a different story. Here we see that flow shapes form across time. And this theme kind of introduces deep time and irreversibility. So here we have water. When it moves slowly, it barely changes the landscape, but in intense flows, the physics of fast-moving water becomes critical. The high velocities generate forces capable of lifting sediment and scouring rock. Engineers describe these flow regimes, and geologists read their long-term signatures in the layered sandstone and the carved plunge pools. The climate determines how often these high-energy events occur, and while sedimentary geology tells us why erosion happens along the particular horizontal layers rather than others. And then statistics helps us reconcile the short, violent events with long periods of apparent stability, showing that the landscapes are shaped not by the averages but by the extremes. And so what we see here is that we have these brief moments of intense flow that shape the landscape for millions of years. And if we take one final look, a neuroscientist might look at attention restoration and stress reduction of being in green spaces. Astronomers look at dark skies and natural light cycles. An economic geologist might look at minerals for green technologies. And a systems scientist might look at trade-offs and thresholds and the unintended consequences. And so here we see another different story for the same place, that places shape people and decisions shape place. So the human brain directly responds to environmental conditions, the sound of moving water, the absence of artificial light, and the visual complexity of natural landscape influences stress levels, attention, and mental restoration. The neuroscience explains these responses, while astronomy highlights the importance of natural day, night, and seasonal light cycles. At the same time, the geological history beneath the landscape determines the presence of minerals, essential for modern technologies, and economic geology connects those deep time processes to contemporary energy systems. So decisions about how resources are accessed feed back into the environmental change, which in turn affects the human well-being. So human health, technology, and environmental systems are inseparable parts of the same system. And so what looks like separate sciences are actually different ways of describing the same connected system unfolding across space, across time, and across scale. And so whether you stand inside the discipline or at the edges, we see that scientific problems are increasingly shaped by the connections and not the categories. The boundaries between the sciences dissolve when anchored to a real-world place. So to give you just a little bit of an introduction to how I'm going to do my talk tonight, bear with me, it's a white knuckle ride, but we'll get there. I do a choose your own adventure style. So in the next slide, I'm going to give you an option of 2 things that we could talk about, and I'll get you to raise your hands and we'll pick one. But we also have interesting side quests, and the spoiler is that those side quests are the work I've actually done, but not the thing that I was going to talk about. But they're interesting, and then we'll pop back to the real story. On occasion, you'll find a QR code. The QR code will give you more information. Spoiler alert, I think the QR code right at the end that goes to my website doesn't work, but it's elizamiddleton.com, you can find it. Okay, 2 choices, side quests, we'll come back. Okay, so for chapter 1, we're going to look at reframing frontiers. We've got the explosion of knowledge or the shift to systems, but first I'll get an idea if anybody wants to do a side quest into managing the Murray-Darling Basin. A couple. Okay, sure, let's do it. Overwhelming response. Let's go, guys. So this was work that I did with the MDBA. They undertook a massive 5-year, $20 million project in response to the fish kill events that happened. This work was done across 4 universities, and my role was to take everything that those universities and government organisations had created together, over 120 deliverables, and turn that into something that people could understand. So people that are making policy decisions, people that are making water management decisions, my dad who runs a farm, so that he can understand what this is. But the really important thing about it is that the express aim of this program was to consider the Murray-Darling Basin as a complex, interconnected system, not separate systems. And so they wanted to integrate the ecological, the hydrological, the climate, and the social and cultural knowledge to inform their real-world decisions. Why it's relevant, I think, to the frontier of science is that in traditional research, questions are often addressed within one discipline, within ecology or hydrology. But here they deliberately structured it around multiple interacting themes. And then the work that I did was to bring those themes all together at the end to come into this synthesis report and identify what were the actions that we need to do to protect the basin moving forward. So it was about synthesis replacing those single discipline answers. And I think that's really important as a hallmark of systems science, approaching the basin as a network of interacting subsystems, not a collection of isolated parts. So we'll go back and go to the real stuff. So hands up for the explosion of knowledge. A couple. What about the shift to systems? Slightly more. Okay, I don't know if I remember the shifts to systems, but let's go. Okay, so scientific frontiers, I think, increasingly involve, as we've already said, understanding interconnected systems. So where the outputs from one model or data set or process are becoming the input to another one, and the outcomes must be compared holistically across environmental and human values. So many questions, I think, can no longer be answered by just looking at the individual components. So if we look at this system, for instance, we're often taught to read it as a movement of water with evaporation, condensation, precipitation, and runoff. It's a correct way to view it, but it's an incomplete way to view it. So what we have is interactions, we have feedbacks, we have scale, and we have outcome. So with the interactions, what we see is that water is interacting continuously with biological, geological, and chemical systems. The arrows in this diagram don't just move water, they also move nutrients and sediment and energy. When we look at feedbacks, we can see that the system responds to itself. So the output becomes the input, and the system doesn't necessarily respond linearly. So some things will be compounded by things that happened before, other things will be dampened. When we look at scale, we see that the same process behaves differently at different scales. So something that happens at a hill slope, runoff controls for soil moisture and plant survival are going to be very different to what happens at a catchment level or in a basin level. And the impacts from those things are going to be different, not only across spatial scale, but across temporal scale. So things that happen across hours or years or decades are going to be different, but they all feed into the same system. And then lastly, we have outcomes. So once we start to consider the interactions and the feedbacks and the scale, the outcomes of the water cycle expand dramatically. And so what we see is that we're not just describing a cycle, we're describing a system that has consequences. So if we go into a couple of examples of this, of things that I learnt about, Hydrobot is one of the things that came out of the Murray-Darling Basin work, and it's an integrated assessment of hydrology-dependent outcomes. It's a toolkit that they built, fantastic toolkit. Anybody can go onto GitHub and play around with it. What it does is it takes in hydrological scenarios and processes them through multiple response models, capturing the outcomes across different themes. So going back to those MDBA themes, it includes the ecological themes, the social themes, and the economic themes. There's also climate as well in that. It links the water flows with the responses, with the broader outcomes, rather than treating those things independently. And so that means that when there is a difference in river flow scenarios, it can be compared not only for hydrology, but the implications for broader environmental objectives or habitat conditions, or in some cases, it's also related to the social and community outcomes of, villages and towns along the riverbanks. So by integrating these multiple models and scales, we're getting these aggregated basin-wide outcomes that really demonstrate how modern science operates across these linked dimensions rather than within disciplinary silos. So science here becomes about the interactions between these processes, not about the isolated behaviour of just one. And when you're managing something as big as the Murray-Darling Basin, that becomes a very important consideration for decisions. There's also the Coorong dynamics model. This is another great one that is a smaller scale, as it's just based in Coorong in South Australia. This is an integrated ecosystem service framework, so similar kind of idea where it is coordinating diverse data sets and modelling approaches to simulate complex system behaviours, but not just single processes. So again, it's linking the hydrology to the water quality and the habitat viability within the Coorong system. And again, rather than running those multiple separate models, it uses integrated tool chains that create these modelled data ecosystems. So the information flows among components and informs the outcomes that matter for the multiple stakeholders at once, instead of it being siloed. So both Hydrobot and Coorong ecosystems show that many of the questions at the frontier of science depend on linking the components across processes and across scales, not just deepening the understanding within one domain. And I think that systems change how the questions are asked. Well, we see that we're looking more at the relationships rather than the isolated variables, that understanding the system means we've got to recognise the feedbacks, the delays, and the unintended consequences of when something is changed here, how it might impact somewhere else. And so the science now, I think, is often less about finding one correct answer and more about comparing possible futures. Okay, next. Choose your own adventure. This is where I grew up, Murray-Darling Basin. I'm a little bit invested in the project, not biased. So we can talk about participation or application of who shapes or what shapes the future of science, or we can do a side quest into Arthur's and koala habitat protection. Anyone up for the side quest? A few people. Okay, great. Thanks so much. I didn't plant anybody, I swear. Okay, so this project was work that I did with the University of Sydney, where I worked with a University of Sydney farm manager. He initiated a landscape corridor for koalas across one of the properties that the University of Sydney owns. So he integrated livestock exclusion with revegetation and habitat design. We worked with the local land service, secured some grants from them, secured some equipment from Wires, and worked with a couple of other scientists to get all this stuff out there, put it in the right places, really blending science with care, with stewardship and infrastructure, with the policy and resources that were available to us to do this on-ground transformation. And then I approached the New South Wales koala strategy, and they came and did some monitoring with acoustic monitors that had confirmed koalas on the farm after 30 years since the last ones were ever recorded on the farm, which was amazing. Koalas were there, and they were hunted vigorously by Archduke Franz Ferdinand when he visited the area in 1893, but that's another story. Anyone like the other story? Hands up. Oh, thanks so much for asking. So yes, Archduke Franz Ferdinand visited Australia in 1893. I think this might be when the war started. He went to the Southern Highlands. He went to Arthursley, which is where this farm is, as part of his world tour, where he famously hunted and shot numerous koalas, noting their surprising passivity, highlighting the historical abundance of these marsupials before significant land clearing and fur trade. I will warn you, don't go and read what's on that QR code if you find it sad to read about how passive these poor koalas were when he shot them out of a tree, but it's all there in his diaries. So land clearing and the koala fur trade followed settlement. We saw the populations collapsed. 600,000 koalas were hunted in a single year. And today's absence feels normal because that loss was gradual, and this is a really striking example of shifting baseline syndrome. And I think this is interesting, but it's also related to what we're talking about, because this is an example of how history and ecology must be understood together to grasp the full impact of human actions on natural systems. So the koala decline was driven by factors that extend beyond ecology alone. There were economic drivers like the fur trade, there were social structures influencing land use, and in this case, Archduke Franz Ferdinand was medically directed to spend time in nature, and he spent that time in nature shooting koalas. So we've got lots of different reasons, and understanding all of these things together is how we get a better picture and a better understanding of the impact that we're having and how these things relate to each other. So hands up for participation, hands up for application. Okay, application it is. So scientific influence, I think, depends on how knowledge is interpreted and applied in real-world contexts. And when I think about it, it always makes me think of a horse designed by a committee looks like a camel, as things get misinterpreted and taken out of, intended interactions. But the other dimension of how it's interpreted of the agency within our science lies in its application. And we've already heard from Dane that it rarely moves directly from discovery to action. There's all these things that happen in between. So it gets interpreted, it gets translated, it gets weighed, sometimes it's not used at all. And the most influential contributions come with really clear explanations. So let's look at a worked example. I love a worked example. So we're going to look at one of the reports from the Intergovernmental Panel on Climate Change. So interpretation here begins with climate change policy, begins with the interpretation of the scientific knowledge. The climate science involves complex data from global temperature records, greenhouse gas measurements, climate models predicting future scenarios. This data is synthesized into comprehensive reports like those that come out of the IPCC. However, this information isn't straightforward. It includes uncertainties and probabilities, and they require careful interpretation by policymakers and scientists and stakeholders. So, for example, the IPCC reports clearly communicate risks and confidence levels, but decision makers must weigh them alongside economic forecasts, social values, and political realities. So interpretation involves framing the science in ways that resonate with the different audiences, from governments to the general public, to foster understanding and support for actions. So the interpretation then leads to the decision. So once scientific knowledge is interpreted, it informs critical policy decisions. Governments decide on emission targets, on investment in renewable energies, and regulations on industries. These decisions are not based solely on science, but also on economic feasibility, social equity, and political will, and they often involve trade-offs. Policymakers must consider the short-term economic impacts versus the long-term environmental benefits and how policies affect different communities. And these things aren't always straightforward either. So, for instance, Australia's commitment under the Paris Agreement was to reduce emissions by 2030, and that reflected a balance between scientific urgency and national interests. Decisions about carbon pricing mechanisms or subsidies for solar and wind, they illustrate how scientific knowledge is translated into concrete actions. So then if we go on to the consequences of the decisions unfold over time and they affect multiple dimensions. So environmentally, we can get effective policies that could get effective policies that can slow global warming, reduce extreme weather events, and protect biodiversity. Economically, they can stimulate green industries and innovation, but may also disrupt traditional sectors like coal mining. Socially, we've got climate policies that can influence public health, employment, community resilience. And importantly, I think the consequences also feed back into the scientific and policy process. Monitoring those outcomes helps refine the climate models and policy approaches, and it creates this dynamic cycle of learning and adaptation. So then if we look in for a couple of examples of what that's done here, we've got the Paris Agreement, we've got the carbon pricing that was introduced in 2012, it was repealed in 2014, and that shows how political interpretation and public opinion can alter decisions despite scientific recommendations. And we also have renewable energy targets to increase renewable energy use, which demonstrates how scientific knowledge about emissions and energy technologies is applied to drive investment and infrastructure changes. So, it's been a wild ride, but we're going to loop back to this beautiful picture so we can all calm down, because I've gotten you all excited, I can tell. If we consider this picture that we looked at the beginning, this beautiful waterfall, I wonder now if you see it differently. I think it's important to note that we've only really focused on this image from the STEM angle as well, and yet there have been many other ways in which this scene would be viewed and understood that would really enrich what we truly know about this place, including the Indigenous perspectives on this beautiful waterfall. And I think regardless of the path that we took tonight, we've seen that science is interconnected, it's consequential, and I think it's deeply human. That's a really big part of it. And so I think this frontier of science isn't just about what we discover next, it's about how we choose to understand, teach, and use what we already know, which is what I've just said there. Thank you.